Hello everyone, my name is Cătălin Negru, and today I will present you the paper called Deadline Aware Scheduling in Cloud Fog Edge Systems. So in this presentation we are going to present an architecture that enables the use case of face recognition in a cloud edge systems where computing is constrained by deadlines. This architecture is tailored for human-robot interaction in which robots capture images of surroundings and use face recognition algorithms to identify and greet people. A robot can make a choice to either use a less compute-intensive local face recognition algorithm at the edge level, or to launch a job in the cloud to run a more powerful and more compute-intensive algorithm based on deep neural networks. At the middle level between the edge and the cloud lies the fog, in which there is a deadline-aware scheduler which acts as a proxy. It facilitates the prioritization of jobs submitted from the edge and the allocation to suitable clusters based on resource demand. We will discuss about the implementation at each level, and we evaluate the performance of the face recognition applications by running a workload that is trained and tested on a well-known label image dataset. We also test the ability of the fog scheduler to launch jobs on time and stay on top of the job queue when strict deadlines are in place. One of the most important features of this model is data management. In the edge, data is collected depending on the rate that the data is generated. It may need to be offloaded in cloud storage. Thus we define a structure called data capsule, whose main purpose is to provide a series representation of the generated data units. What should be mentioned there is that it's an optional field which represents the data content. If data needs to be stored in the cloud, then the next must be set to storage, and the data will be appended in the data capsule. If the edge needs to run an algorithm, it must set the context to the corresponding algorithm, and set requires arguments for the algorithm. In this case, there is no data in the data capsule. In the first example, an edge device decides to run an algorithm in the cloud on data. In the context, the algorithm is indicated to be of fog face recognition, and this will help the fog layer to schedule and identify the corresponding clusters and the arguments, data allocation for instance, and the deadline are set. In the second example, let us consider a data capsule generated from the edge that requests data to be stored in the cloud. In this case, a process in the edge needs to complete the mandatory fields, context and data, but also metadata such as location, and then send the capsule over the network. The edge layer consists of devices that have the main responsibility of collecting data and sending it at higher levels of the architecture. These devices can be robots, mobile devices, and even sensors. More powerful devices, such as robots, can even run lightweight jobs locally if resource constraints are met and batteries allow. The fog layer consists of the scheduler and access point. This layer is responsible of uh, performing deadline-aware scheduling of jobs, and it's responsible of forwarding data to the corresponding storage using publish subscribe messaging protocols, and also service discovery, which are based on the context if it identifies which clusters can run which jobs. Edge devices have batteries and resource constraints, and powerful machine learning algorithms such as deep learning are not suitable at this level. However, simple algorithms such as face recognition using aging faces are suitable. The idea is that images are pre-processed, converted to grayscale, the faces are centered and scaled down to a fixed size. Then, using the algorithm on the right, the images are decomposed to a set of significant features called aging faces, and this model is kept locally at the edge once it is trained. Other techniques such as support vector machines can be used for testing. When a picture of a person is taken, it is processed and the algorithm runs it through the classifier and a match is identified. We have implemented a deadline-aware scheduler in the fog for the proposed architecture, which respects deadlines from the edge. The algorithm has two stages. In the first stage, we identify the jobs with the closest deadline, and in the second stage, we identify the cluster that is most suitable to run jobs based on preferences from service discovery service and the cosine similarity for resources. These two stages are in a scheduler function that is executed uh, periodically. On line 1 to 3, we get the ordered jobs queue from each context, the list of possible contexts, and the set of available clusters. On line 4 to 12, we identify the job with the closest deadline. In the rest of the algorithm, the scheduler determines the cluster on which the job must be run. This is done using cosine similarity to find the cluster which has suitable resource availability to the resource demand of the job. Once the pair, job and cluster, have been determined, the scheduler will launch a request to the specified cluster to run the job. In the cloud, we employ a face recognition algorithm using deep neural networks in Apache Spark. Data is labeled in HDFS and consists of directories where each directory represents the label, for instance, name of the person, and contains multiple pictures of the person. The application loads this data set into data frames, which is specified in line 1. Then the application creates the machine learning pipeline and computes the model based on the trained data frames. When the application receives a notification that it should run an image to the model, it will read the image from HDFS, pass it to the model, get the prediction, and send back the prediction to the fog layers. So these are the results that we have obtained from launching 1000 face recognition jobs, which are being split such as 25 critical priority jobs, 25% high priority jobs, 25 medium priority jobs, and 25 low priority jobs. And compared to standard FIFO scheduler used by Spark and Hadoop. The FIFO scheduler does not take into account deadlines, and this means that the most critical and high priority jobs don't finish on time. This is confirmed by the result, which shows that FIFO gets close to 70% completion rate of the jobs on time. The fog scheduler takes into account the deadline imposed by the jobs and thus achieve a very high completion rate on time, about 95%. This result shows that our fog scheduler is well suited to the scheduler jobs based on deadline. So these are the data set that we use for the results, consisting of over 30,000 images of 5,749 people, and we selected people that have over 80 images and split the training and testing. We have preprocessed images for edge, which means to convert to 64 by 64 grayscale and center on face, and we collect the results using performance analysis tool. On the left side, there are the performance result of the face recognition algorithm. On the edge, we pre-process the label faces in the wild dataset. We turn them to grayscale, center the images on the faces, and scale down on dimensions. We can observe the CPU and memory utilization at each time period. The first observation is that the algorithm is fast and runs under 10 seconds. Another observation is that the resource utilization is minimal and there is barely any noticeable impact on CPU and memory. Thus, this implementation is a good candidate for edge computing. However, the drawback is that the edge devices are responsible for taking the pictures of people and preprocessing these pictures, which might add additional overhead. On the right side, we observe the performance result of running the face recognition algorithms using deep learning in the cloud. No preprocessing is done at this level, and the algorithm is trained to be on the dataset as they are. We observe the CPU and memory utilization at each point in time. The workload is very memory intensive, while the CPU on average does go over 20% utilization. So the total time of the experiment was 1 hour, most of which was training, and the last 10 seconds was the testing stage. At the beginning, there is a CPU spike when all the images are loaded into data frames, and next the training starts. There is a constant rise in memory utilization that goes up to the full cluster capacity. We use 4 machines of 4 cores of 2.6 gigabytes and 60 bytes of RAM, 6 bytes of RAM, gigabytes of RAM, and 1000 gigabytes SSDs. So, in conclusion, we presented the concept of data capsule and a cloud edge architecture on which we implemented a deadline aware scheduler for face recognition using aging faces and neural networks. Thank you very much for your attention.